So in the last segment, we learned all about greatest common divisor, what it means to actually divide something, how to find those divisors, and etc. In this particular segment, we're going to explore the idea of divisors and how to find divisors a little bit better. So let's start with a simple question. Let's start with the question, how many divisors does, sorry about my handwriting, oops, does 24 have? All right, so the most straightforward way to do this would be to, say, list them. All right, so if I make a list, well, obviously 1 is a divisor, and we talked about partners before, so 1 has a partner, and 1's partner is 24. All right, 2 is a divisor. 2's partner is 12. 3 has a partner. 3's partner is 8. And 4 has a partner, and 4's partner is 6. All right, so if we list them, that's all of them. If we list them and then if we count them up, we get 1, 2, 3, 4, 5, 6, 7, 8. So let's say how many divisors, that's my shorthand for how many divisors, and the answer is 8. Alright, so if the question was, instead of how many divisors does 24 have, if the question was how many divisors of, let's see, 5, 7, 1, 4, 5, 0, so 571,450, if that were the question, then listing them would be kind of a challenge. Matter of fact, it would be really sort of annoying. So perhaps there's a better way. Now we are going to find all the divisors of 571,450, but we're going to do it, or the number of them. We're not going to find them all. We're going to find the number of them, but we're going to do it in a slightly different way. So before we do that, let's look at the first problem, and let's look at it slightly differently. So instead of just listing the factors, or the divisors, what if we first just prime factored? Okay, so what if we first just prime factored? So let's prime factorize 24. Okay, so prime factors. Some of my vertical lines are not working out quite so well. Okay, so prime factors of 24. Well, 1 is not prime or composite, so we leave it off the list. But we have 2. 2 goes in. Matter of fact, 8 goes in. So if we look here, 8 is 2 cubed. So we know we can get this as prime factors are 2 cubed and times 3. Okay, so how are these prime factors, or how are these factors formed, and what's their relationship to the prime factors? Okay, well, how about 1? Well, 1 is sort of 2 to the 0th and 3 to the 0th, right? There's no factors of 2 and there's no factors of 3, leaving only a factor of 1. That's 1. All right, well, what about 2? 2 is equal to 2 to the first. Okay, 3, on the other hand, 3 is equal to 3 to the first, duh. 4 is equal to 2 squared. Okay, so we got 2 to the first, 2 squared, and let's actually jump ahead to 8. 8 is 2 to the third. Okay, now what about 6? Well, 6 is actually 2 to the first times 3 to the first. And then what about 12? 12 is 2 to the second times 3 to the first. And 24 is 2 to the third times 3. Okay, now if you were keeping track there, you noticed that we just got every combination of we have 2 to the 0, 2 to the first, 2 to the second, and 2 to the third. Come on, there we go, 2 to the second, and 2 to the third. Those are the possibilities for 2. And then here, for 3, we have 2 possibilities. We have either 0 3s or 1 3. Now, if we put together all possible combinations of 0, 1, and 2 for the 2s, and 0 and 1 for the 3s, we get 4 times 2, which is 4, whoops, wanted to do a different color there. So, wanted to do 4, okay, 4 times 2 is equal to 8. Now, is that a coincidence that 4 times 2 is 8 and there are 8 divisors? No, it's not. And the reason, we're not going to prove this, but it's kind of cool. The reason is that there are every factor, every divisor of 24 must be, well, yeah. So if a factor contains a prime number, that prime number must also divide, since it divides the factor, it must also divide the major number, which means that any prime number that's a factor of, say, 12 must also be a factor of 24. Therefore, the primes in the prime factorization of our number and the primes in all the factors must be the same. That's one part of it. The second part is that the prime factors can go in any number of times between 0 and the number of factors. So just by looking at all of the combinations of the factors, considering the possibility that we don't use the factor at all, which is the 0, then we end up with the number of prime factors. So our method then in general, let's move this out of the way. Whoa, that was interesting. We'll move this down just a little bit. Matter of fact, we are going to cut it so we can paste it on the next page. Okay. In general, if we have a prime number. Okay, so if we have our number, we factor our number into prime factors. Whoops, I need a pen, sorry. So we have a number n, and n turns out to equal, let's say here, prime 1, and prime 1 has some exponent, say, q1, and then we have prime 2. Prime 2 has some exponent q2, and then prime 3, etc., has some exponent q3, and then this goes on for as long as it needs to. In particular, let's say maybe that there are m prime factors. So m as in Michael, and then q as in Michael. Okay, so the number of divisors then, let's say number of divisors of n is equal to Q1 plus 1, come on, plus 1 times Q2 plus 1 times Q3 plus 1. All right, so I give more credit to Sol Khan than I originally did. Anyway, Q1 plus 1 times Q2 plus 1 times Q3 plus 1, and then this goes on and on. To the point where we have Qm plus 1. So you take the exponent, you add 1, and you multiply it. All right, that gives you a number. Actually, there's some nice shorthand notation for this. So it's you've probably heard of sum notation. There's also product notation, which we use a pi symbol for. And we're going to talk about this in a little bit. So the way the pi notation works is you have, just like some summation notation, you have an index, and let's call the index in this case I, and I is going to start at some number, and in this case it's going to start at 1. It can start wherever it likes, but for our product it's going to start at 1, and it goes, in this case, up to the highest number, which is m, and as usual with summation notation, it increases by 1. So it goes from 1 to m, and instead of adding all of the terms created by doing this, you just multiply all the terms created by doing this. So what we're going to multiply is we take q sub I plus 1. All right, so that is our formula for the number of divisors of a particular number n. You just take the product of one more than each of the exponents of the prime factors. Now, as a quick aside here, this relies, for this to work, this relies on this prime factorization being, first of all, existing and also being unique. Now, we're not going to prove this in class, but this is actually the fundamental theorem of algebra. I'm sorry, fundamental theorem of arithmetic, is that every number can be factored uniquely into a product of primes. Kind of a cool, well, it's very obvious, but in math we need to make sure that everything, even the obvious, is provable from first principles. So if you're interested in how to prove, or interested in just reading a little bit more, you should Google the fundamental theorem of arithmetic and check it out. All right, let's pause here, and then we will go on to applying this to our problem with 571,450.